Okay, guys, thanks a lot. Um, I hope everybody had some luck trying to get up on the stuff up on Great Scope. Any questions about the format of the quiz? The rest, the other seven are going to be kind of in this format. Again, one or two.
Are they gonna have hints?
I'll try to throw in hints because one of the things. By the way, thanks to everybody. I think almost everybody responded with really good input for getting to know you, the questions, etc., strengths, and a bunch of you guys answered that you had a hard time. You kind of have a tendency to get wrapped around the axle with problems, etc. So I'm going to try to have hints for you guys, point you in the right direction. So hopefully it's not going to be like some kind of an IQ test. It'll be like if you've done the homeworks, get some hints, you'll be okay with the quizzes. Okay, so anyway, it's this whole we went to online, as you guys know, halfway through last semester. It wasn't pretty. Probably it wasn't pretty from this side. Probably wasn't pretty from you guys. So I'm just trying to figure out like what the how to change stuff out. So the things we really changed, I really changed was the quizzes. Just trying to get kind of on a more regular basis as opposed to having a bunch of sort of the big events. Okay, so let's get started, guys. And then, by the way, on the the class, I think it's actually more on the class schedule. I have readings assigned, for the next couple of weeks, and suggested homeworks. And it's a way to try to get you guys focused on what I think are the important issues. For example, the next 2 weeks we're going to be covering chapters 1 and 2, and what I'm going to do is I'm going to go through semiconductor physics and PN junctions, those kind of things, pretty quickly, and in an effort to get to circuit design as fast as we can, because this is primarily a circuit design class, but the semiconductor physics can get really involved. I got my PhD in that area. You could spend years and years talking about it, thinking about it. So I'm going to go through it really fast, but hopefully in the way of try to get you guys the homeworks, it'll give you an idea of what sections are important and what not so important in the text, and same with the reading. Okay, so let me share my screen here. And the other thing I'm doing is I'm trying to have sort of a hybrid method of having having slides, but I'm going to write on the slides. So hopefully that'll work with you for you guys. And I'm going to, if I can get all this stuff figured out, I'm going to basically save my writings. And anyway, they'll be recorded, etc. Okay, so let's still thinking about the background for the class. What you guys are probably used to seeing are circuit elements are things like resistors, capacitors, inductors. And in this class, we're going to be talking about a different class of circuit elements that are going to actually make for a much richer set of circuit functions. In fact, most of the circuits that you see now are made out of those. And there's, as far as I'm concerned, there's a couple of differences. Okay, so let's look at the resistor. So it has an equation like V equal to IR. And if I was going to plot this, you'll see a lot of these plots of voltage versus current you'll see it for transistors, for diodes, but right now I'm just drawing it for a resistor, okay? So if I was going to have I is equal to, I always have to write this, I is equal to V over R, meaning that if you look at this equation, if V is positive, we have a linear relationship between voltage and current given by the slope of 1 over R. Okay, that wasn't such a linear, but yeah, it's just a line here, not curvy. Okay, and then if I have a minus V, I'll get, the current will go in the other direction. You get a kind of a minus V, will give you a minus I. Or, the other way to look at it is if I had a voltage source and I had a resistor, I could hook it up like, I'm just going to call this 1 and 2. So I could hook it up like this, or I could hook it up like that, basically flipping 1 and 2, and I'd get the same result. So it's kind of this linear, it's, I guess, what you think of it as being a linear type of component. And same with like if you think about a capacitor, okay, now a capacitor is a little different. So it's more like, depending, if you want to leave time out of it, it's sort of dependent on charge. And so how should we do this? If I was going to draw capacitance versus voltage, I'm sorry, I was going to put charge versus voltage. As I change the charge, basically you kind of get, as I increase the charge, you get a higher voltage with this C relationship here. Okay, so as I change the charge, voltage is Q is equal to C. And if I flip, so if I had, and I'm going to put a current source here because I don't know how else to do it, because it'll be a matter of time. And then if I flip the capacitors the other way, it'll discharge. So these are linear type circuits, okay? But I'll draw a diode for you guys. You don't know what it is yet, but we'll go into it. But here's a symbol for diode. So the first giveaway is, you see the symbol for resistor, it's symmetric, so it doesn't seem to have a top or bottom. Same with the symbol for capacitors, symmetric, doesn't seem to have a top or bottom. But a diode, it's not a symmetric looking picture. It definitely has a top and a bottom, or bottom and top, whatever. It has two sides, okay? And it will work very differently depending on whether I have it hooked up like this to a voltage source, or like this to a voltage source, okay? In this case, it'll look like an open circuit. So it'll look like as if I have a voltage source with nothing connected. And in this case, it'll look like a short circuit, as if I've just shorted across the voltage source. So that's one thing, is linearity. So these things like R's, C's, inductors are linear, and diodes, transistors, those are things we're going to be covering in this class, are nonlinear. Okay. The interesting thing about, but it just says that voltage versus current characteristics of these devices is nonlinear, but doesn't mean that you cannot design very linear circuits based on these devices, and that's part of the complication. And then you can also make very nonlinear devices like logic gates, which are actually extremely nonlinear circuits, but they can let us have ones and zeros as opposed to a bunch of voltage steps. Okay, so that's one big difference. Let's see if I can add. Sorry guys, I'm still okay. There. Oops. Sorry guys. This will get better hopefully. Okay, so that was one thing, which was linearity. The second thing that's different is you really, it sort of matters, but for a resistor, a capacitor, you guys didn't really care what they were made out of. You just saw them as having these equations. Again, a resistor was we saw a resistor, or I always think of it as a conductor with a certain resistance. But if you put a voltage across a resistor, some current will always go through it. Okay, it always conducts, no matter, at least the model we have of it, no matter the temperature, no matter what, you'll get, it's always conducts, so it's a conductor. It's an example of a conductor. Wire, that's a conductor, it still has some resistance, okay? And then a capacitor is an insulator, always. So no matter what temperature, etc., you are not going to get a current going through it. It's always going to charge, is going to pile up on one side and the other. So it's an example of an insulator. Okay, so the semiconductors, so this is the second difference with this class compared to what you'd seen before, is a conductor some of the time. So, or anyway, so this is another complication. So we actually dig into what it's made out of and look at a structure of the elements that we're going to be using, where we didn't really do that in classes about resistors or capacitors. You didn't really care about how they were made. You were just sort of looking at them as circuit elements. So those are the big two differences. Linearity versus nonlinearity, and semiconductor versus conductor insulator. Okay, so let's talk about, let's see, okay. So let's talk about semiconductors. And again, semiconductor physics, huge area. I think most of, I don't know which one of you guys was interested in getting into the semiconductor business. I think if you are, hopefully there's classes you can follow up with this. I know in the VLSI class, we're going to be doing a little bit more, but most of you guys are going to be interested in just doing circuit design. And you just need this as a background to understand how these devices work and why they work that way. Okay, so in terms of semiconductors, we're going to talk about three main things. Okay, so the three main things are basically how you get conduction through the device. These are made by, the conduction happens by charge carriers in a semiconductor crystal. We're going to talk about how we can dope, quote unquote, dope the semiconductor with other material to make it more or less conductive. And then we're going to talk about the mechanisms for how that current happens in a semiconductor. In a conductor, well, in an insulator, there is no current conduction, so we don't worry about that. In a conductor, we just think of the conductance as being sort of a drift component. So you put an electric field across a wire and you get current going from one side to the other. For a semiconductor, there's still this drift current as a function of the electric field, but there's also a diffusion current. We'll talk about those. There's two main methods of current carrying. And so you basically need a background understanding of all these three components, which is what we'll talk about today, for us to understand how a PN junction works. So a PN junction is, it's putting two semiconductor types, and I want to look at it, I guess, two types, and with it, you're making the most simple type of semiconductor circuit element, which is a diode. So once that'll be for sort of the remainder of the sessions coming up, as we'll talk about these PN junctions. It talks about reverse and forward bias. So this PN junctions may make this circuit element a diode that has certain characteristics of voltage versus current, sort of like that. Okay, and then we'll talk about if you're going to just use a simplified circuit model, what are the different options about that? Okay, and then like a transistor, a bipolar transistor is really two. You can think of it as two PN junctions that are cross-talking with each other, that are affecting each other. They're back to back, and MOS transistor, which is the other transistor we're looking at, also uses the PN junctions. So PN junctions are the key element for all semiconductors. So that's what we'll be looking at. Okay, so let's talk about, let's jump into the periodic table. Okay, so this is your periodic table out of chemistry. We've just looked at group 3, 4, and 5. Okay, and the key thing here is the key element in the semiconductor business is really silicon. And it has a lot of magical properties, but it's really kind of, germanium is also used, but very little. Almost all the stuff, all the semiconductors in your cell phones, almost everything is made out of silicon. Okay, and so that's an important thing, that silicon is a group 4 element. And the other thing we're going to talk about a little bit later is how we can use group 3 and group 5 elements to affect the performance of silicon. Okay, so Silicon Valley, I don't know. You guys have heard of silicon, that what makes our world go around. Okay, so what's special about silicon, and what makes it a semiconductor? Okay, so if you look at a silicon, a group 4 element basically means that silicon has 4. If you just look at a silicon atom, it has 4 valence electrons. So valence electrons are electrons at the outermost shell of an atom, and they are the easiest electrons to strip away. Okay, so the valence electrons are the easiest ones to strip away. And if you make a crystal, so if you put a bunch of silicon atoms next to each other, okay, they will share covalent bonds with each other. And because each one has 4, the way the crystal structure sits is each silicon atom will have 4 neighboring silicon atoms. So all the covalent bonds, basically get a complete sharing of covalent bonds, means that you get this crystal structure, and it's at 0 temperature, or at very low temperature, this thing acts as an insulator, because there aren't, sort of a perfect crystal, there aren't any stray electrons to conduct any kind of current. Everything's spoken for. All the electrons are stuck in these covalent bonds with neighboring atoms. Okay, but what happens, and the reason silicon is called a semiconductor, is as soon as the temperature goes up a little bit. So let me take a segue to talk about temperature in this class in the semiconductor business. So the temperature is in kelvins. Okay, that means that so room temperature is about 300 Kelvin. Okay, so 0 degree Kelvin is, minus, I think it was 277 Celsius. So it's basically like very, very cold. So when we're talking about higher temperature, by the time you're at minus, I'm just going to make up numbers, but say minus 200 degrees, so at 77 Kelvin, you already have, you already have electrons floating around. So at, minus 200 degrees Celsius, this thing is still already acting as a conductor. But as it gets closer to 300 degrees Kelvin, which is room temperature, it's acting, has a much larger number of free electrons floating around. And, as it gets hotter, it'll have more free electrons. So, by the way, as an aside, those of you who will eventually work in the aerospace business, maybe the DoD business, there is a lot of work in, thermal cameras, et cetera. They are working very close to, usually they're working at 77 degrees Kelvin or something like that. So they're working, so these are cooled elements. And so they're still used as semiconductor elements, okay? But anyway, as temperature, yeah, go ahead.
Real quick.
Is it William?
I noticed, yeah, wait. On the periodic table, the other elements that have 4 valence electrons are also carbon and germanium, right?
Yes.
What makes silicon preferred over those?
There's a couple of things. One of them is the band gap of silicon, and we'll talk about what the band gap means and what it'll lead to just in a couple of slides. But the band gap of silicon is at a happy place where, especially at room temperature or typical operation. So, I talked about Defense Department or whatever, but most of our electronics runs right around room temperature for good reason, because that's where we're comfortable. So most of cell phones, automotive parts are running between, say, 0 degrees Celsius and 100 degrees Celsius or 80 degrees Celsius. And in that sort of place, silicon, its band gap means that you don't have too much conduction. So you still are pretty good as a semiconductor. So carbon has a higher band gap, meaning it has fewer electrons in that temperature range. And germanium has a smaller band gap than silicon, means that it has too many electrons floating around, which is kind of makes things hard to deal with. So the band gap is very important, but even more important, so that's band gap is very, very important, but even more important as far as MOS transistor goes. So we talked about diodes, bipolar transistors, and MOS transistors. These MOS transistors, which will be the last thing we get into, are by far the majority of all the chips in your cameras, in your cell phones, in your computers are made from these MOS transistors. And those MOS transistors, it stands for metal oxide semiconductor. That oxide, which is an important part of the transistors, as we'll see, is made out of silicon dioxide, which is a really nice insulator. And it's the enabler for silicon to be used as a MOS transistor. And neither germanium nor carbon have that nicely performing oxide. So those are the two main reasons: is the band gap and the fact that there's a nice oxide that goes with silicon. Did that make sense, William?
Yes, thank you.
Okay, sure. Okay, so let's see. Okay, so all right, so that was the electron floating around, and it gets freed up even in a perfect silicon lattice, only silicon atoms in this lattice. Some temperature, you'll have electrons floating around. So it'll be conducting somewhat, and as the temperature goes up, it's going to get more and more conductive, okay? And so, but the other interesting thing in semiconductors is a concept of a hole. So you have an electron, which is a negatively charged conductor in, this is a negatively charged element, okay? And then in a semiconductor, we have this concept of a hole, which is a lack of an electron. So if, say, an electron gets freed up in, say, in this guy, this electron sort of flew off at some point, right? So there's a lack of an electron there. And so this is so-called a hole, which is means, you know, there's no electron there. And this guy can also move from atom to atom, as you know, it can swap the electron with this guy, and the hole, or this lack of electron, can move from place to place in the lattice. So the holes, which are the lack of an electron, provide what looks like a positively charged element that also leads to a current. And we'll see why that's important a little bit later. So anyway, you have electrons and you have holes. As soon as you have an electron generated, you'll also have a hole. Okay, I'm going through this fairly quick, guys, because you know, as you'll see in the sign reading and the problems, this is just mostly like background stuff. I'm anxiously trying to get to PN junction stuff where the meat is at. So anyway, if it feels like it's going too fast, it's okay. I'm just kind of this stuff. I'm going to point out to you guys what the important concepts are. Okay, so as sort of answering, go ahead.
I'm sorry. I think my internet cut out for 1 second. Could you repeat like the last few sentences you said?
Just last few sentences.
Yeah, just the last few sentences.
Yeah, I was just saying, if it seems like I'm kind of going fast through a lot of deep material, it's because I'm anxious to get to the PN junction, the second half of chapter 2. And so this is like a lot of stuff, but I'm going to just point out to you guys what's important here. As you'll see in the homework assignments and the reading, you know, this is sort of background information. There's a few things that are important and I'll point out to you guys. Just stuff.
Okay. Thank you.
Sure. So going back to William's question, so if you look at how many electrons or free carriers are in a semiconductor, we come up with this really general equation here, okay, which is this guy. Okay, so you don't need to memorize this equation, okay, so I'll point out, but there are some key elements here, okay? So N sub I is the density of free carriers. So it's the number of electrons or holes. It's mentioned in electrons, but it could be electrons or holes. But let's talk about electrons. Number of electrons per centimeter cubed. So it's a number of free carriers per unit of volume, okay? And you get this equation here, 5.2 times, I think there's some times is missing here probably, times 10 to 15th. And here's some of the dependencies, okay? So notice there's a dependence on temperature here. That's temperature to the power of 1.5. So not temperature squared quite, but it's up there, okay? And then there's an exponential relationship here with temperature on the denominator. Okay, so that's kind of working against this guy. You have a power of temperature to the power of 1.5, an exponential of 1 over t. Okay, but in aggregate, this temperature will make this density, this charge density, go to 0 at 0. Well, at 0 temperature, this Ni will just equal to 0 because this guy will make it so. Okay, as you step up gradually, your number of free electrons will go up with temperature, okay? The other thing that's part of this equation is this E sub G, which is this band gap I was mentioning to William about, and that depends on the particular material. The band gap of silicon is 1.12 electron volts. Okay, I got it down over here. It's in your book. And so this is an electron volt is a unit of energy. And so it's kind of like a joule, but given in terms of electron volts. So it's basically, indicates how much energy you need to get a sort of electron from the valence band to the conductance band. Okay, so the larger this band gap, the harder it is to create an electron hole pair. So if you look over here, you'll see for a diamond, which is an insulator, the band gap is 2.5 electron volts compared to silicon's 1.12. And for conductors, you get a band gap that's maybe 0.1, 0.2 electron volts. But for a typical semiconductor, the band gap's 1 to 1.5 electron volts. I think for germanium, I think it's something like 0.67, I want to say, electron volts. And so germanium you see this E sub G is in the exponent. So that means that germanium, because it has a lower band gap, will have a different number of electrons. Okay, and then finally this K, you'll see also repeatedly, is the Boltzmann constant.
Professor,
Yeah.
on that equation, I think there should be a negative sign at the front of the E sub G.
Thank you. That explains why you'll have, for a larger band gap, a smaller band gap, you'll have more current. Thank you. So let's see. So K is a Boltzmann constant, which is just absolutely a physical constant. So you'll always have that. Okay, so these are the elements in this free electron density equation. Okay, so a couple of points. So things to know or remember from this. Sorry guys, this PowerPoint is, I think when I put it on my iPad, it acts a little funny. So, so one key number here is that the free electron density, this is for silicon, at room temperature, which by agreement is 300 degrees Kelvin, is 1.08 times 10 to the 10th electrons per centimeter cubed. So I don't think you need to memorize it, but it's a good number kind of to keep in mind. But the thing you guys need to know from this is at the temperature much higher. I mean, I said this is probably something like 330 degrees Celsius because 600 Kelvin. It goes up by 5 order of magnitude. So it went from 10 to the 10th to 10 to the 15th. So it goes up significantly. It changes significantly with temperature. So remember that. The main thing to remember from this equation is that the free electron density, this n sub I, changes with temperature very rapidly, and it goes up with temperature. Okay, because most of the time we're going to be talking about silicon, so the band gap's not going to change. Boltzmann's constant, of course, is not going to change, the physical constant. So the one thing that will change is temperature. Okay. All So we talked about how, so that's one way you can get a semiconductor to be more of a conductor and less of a insulator. So it's temperature. Okay. The second way is so-called doping. Okay. So going back to our periodic table, remember that I said the group 3 and group 4 will be important. And so what you can do with these two is starting with a silicon crystal. You can, I'm not going to talk about how you do this, but you can insert things like phosphorus, which is a group 5. So phosphorus is a group 5, which means it has 5 valence electrons. So you can put a phosphorus atom in this lattice. And this phosphorus atom, because it has an extra valence electron, even at lower temperature, it'll have this free electron available that's going to be floating around in the crystal lattice. Okay, and then you can do the same thing with, this is boron. Boron is a group 3 element, which means that it only has 3 valence electrons. So if it's sitting between a bunch of silicon neighbors, it's always going to have a lack of electron or a hole available. So it has more holes. So if you put in a bunch of phosphorus into a silicon crystal structure, it'll have more electrons. Okay, and that's a so-called N-type. So this is something you guys should remember, is that if you dope semiconductors with a group 5 material, it'll have more electrons, and that's called an N-type device. So it has an excess of electrons. So notice one thing, before we did this, right, here we had every time from this equation, every time you created an electron, you also ended up with a hole, right? Because you had a pure silicon crystal, and you couldn't create an electron without a hole. So you could increase and decrease the density of free carriers with temperature, but you couldn't make it kind of a selective thing. But with these P and N types of dopants, you can make the material have either more electrons or more holes in the same temperature. And so the holes, if you have something like a boron, which creates more holes, it gets to be called a P-type material. Okay, guys, I'm going to stop it here because we're run out of time, and we'll pick it back up talking about how that affects the electron and hole densities. Any questions? Okay, if not, thanks a lot, and talk to you guys on Thursday.
Oh, Professor?
Yeah.
These slides, do you have them in Blackboard? Or just recording?
I think I put them up on Blackboard, did I?
Yeah, yes, they are.
Yeah, they're
I'll
on
just import.
Yeah.
Thank you.
Sure, absolutely.
Thank you, Professor.
Professor,
Thank you, guys.
uh,
Take care.
Professor,
Yeah.
are we going to be getting feedback off of the quiz we just took today?
Yeah, I'll be looking at those. Yeah, you will be.
How are you going to do it? Like, is it going to be through Gradescapes, or is it going to be like an email saying like how we did?
Boy, I'm going to try to do it through Gradescope, but if that fails, it'll be through email.
Okay, all right, thank you.
Okay, thanks.